we'll be starting with DC generators, and similar to DC motors, a DC machine can be operated basically as a generator or as a motor, and the construction is almost similar. There's hardly any difference. The same motor can be used, the same machine can be used as a motor, as a generator, and similar to DC motors, we'll be having different types of configurations that will be different types of DC motors that will be studying separately excited DC motors, DC generators now, and then we'll be having the shunt field DC generator, behind the series field DC generator. We'll be studying the cumulative compounded DC generator and the differentially compounded DC generators. We'll be studying their equivalent circuits, and we'll be studying their the terminal characteristics. When I talked about the terminal characteristics, I said to you that terminal characteristic basically indicates the output profile of a machine. In case of a motor, the output profile is basically speed and torque. So we have the speed torque characteristics particular of a generator. The output characteristics will be voltage and current. So in such a case, in generators we'll be studying the VI characteristics. So starting with the first, we have separately excited DC generators. So what are separately excited DC generators? We know that in case of separately excited DC generators, unlike the shunt, in case of motor configuration, the shunt motor and the separately excited DC motor, they were similar. They have the same torque speed profile, and there was not hardly any difference there in operation. But here there will be some distinguished characteristics that we need to understand. Separately excited DC generator is the simplest of the DC generators. Now if we talk about the equivalent circuit of this, we have the field winding. Fine. So there's no difference here. You'll be applying the field voltage or DC voltage across the field windings, having inductance of LF and resistance RF. This generator will be moved using the prime mover. The armature of the generator, DC generator, will be moved using the prime mover, and on the armature side, the only difference you will exactly be showing is in the direction of current. So it's actually the direction of current that will distinguish between a DC generator and a DC motor. Direction of armature current rather. So operation simple. You have the field windings producing a magnetic field and a prime mover. External prime mover, it can be a turbine or any such device that actually moves this, that actually rotates this device, that actually rotates the armature of the DC generator. So you have a rotating armature, rotating circuit placed in a magnetic field. So current will be induced in, so voltage will be induced in this, that is EA, and as soon as we load this generator, current IA will be flowing through the armature windings. So uh, uh, that's the operation of this motor. Now what we need to do is we need to understand this plot Vt versus Ia. So simply apply the KVL to the armature circuit. We know Ea will be equal to, now this is a generator. In case of a motor we said Vt is equal to Ea plus IaRa, but now the direction of current has reversed, therefore Ea is equal to Vt plus IaRa, which implies Vt is equal to Ea minus IaRa. Fine. In case of motor, it was Vt is equal to Ea plus IaRa. In case of a generator, it will be Vt is equal to Ea minus IaRa. So we need to plot Vt versus Ia. So we're using this equation, using Vt equal to Ea minus IaRa, if we plot this is Vt, this is Ia, and Vt is equal to Ea minus IaRa. At Ia equal to 0, Vt will be equal to Ea. So Ea is, say for example, 230 volts. So it will start from here. As Ia increases, Ea minus IaRa basically will decrease. So it will be a straight line, a linear line that basically shows decreasing terminal voltage as the motor is loaded. So this is your terminal characteristics. This is your terminal characteristics under normal operations. Now what happens is, as we increase the armature current, as the armature current in the motor increases, as the armature current increases, the MMF produced by the armature will also increase, therefore reducing the main magnetic flux produced by the field windings. So as Ia increases, the main magnetic flux decreases, because this is actually simple principle of the armature reaction. As you increase the armature current, the armature MMF increases, that will cancel out the main magnetic flux, the flux reduces, and if flux reduces, Ea is called K phi omega, Ea will reduce. So there are two effects happening simultaneously. One, Ia is increasing, and two, Ea is decreasing. So instead of having this graph, we'll actually be getting a graph like this. So if this were a straight line, this effect basically shows, and this is called Ea. This effect is with armature, is without armature reaction. And this is your Vt versus Ia profile with armature reaction. Therefore, this is actually simply IaRa drop. This effect is the armature reaction drop. So the actual profile without a compensating winding will look like this. But since we will be incorporating compensating windings and interpose in a DC machine now, so we expect that our Vt versus Ia graph will be a straight line, and only the IaRa drop, that's actually unavoidable, the copper losses, will contribute to the drop in the terminal voltage. So the available terminal voltage to us is always less than the actual generated voltage in a DC generator. So whatever is generated is not available to us. Vt will be always less than the actual voltage generated. So that's actually something that we already are familiar with. Now, DC generators are not used much widely nowadays. DC motors still find some application, but DC generators are rarely used, and there are a lot. There are many. You see, there's very less applications based upon directly run DC generators. So this is the terminal characteristics of a separately excited DC generator, and it's a simple straight line, straightforward. Now talking about we in DC motors we talked about speed control of motors. Instead of talking about speed control, we'll be talking about terminal voltage control. Vt is equal to EA minus IA RA. We cannot control IA, we cannot control RA. So the only way we can actually increase or decrease the terminal voltage is by increasing or decreasing the armature, the generated voltage EA, and we know EA is equal to K phi omega. So again, if we want to change EA, we can change the flux, and we can control the speed of rotation. So Vt can be controlled by speed of rotation. So you have a prime mover run a turbine, or a prime mover basically running the basically rotating the armature. So if we are able to increase its speed, EA will increase, therefore Vt will increase. Fine. An increase in speed will mean an increase in terminal voltage, or a decrease in speed will mean a decrease in the terminal voltage. Now there's a disadvantage with speed with this method. More or less the prime mover is actually fixed to the DC motor, unless there's a gear mechanism wherein we can change the speed of rotation. This method cannot be employed for speed control. Other method that we can use is controlling the field of the generator. So if we can increase the flux, again Vt will increase, or if we decrease the flux, Vt will decrease, because flux actually decreases the generated voltage. Flux decreases the generated voltage, in turn that decreases the terminal voltage available to us. Now flux decrease means actually IF is decreasing in the circuit. That means actually we are incorporating more field resistance. We are incorporating more resistance. We are decreasing flux. We are therefore being able to control the terminal voltage, or we can increase the field voltage so that the field current in the field line is increased. That will increase the flux and therefore the terminal voltage. So this is about separately excited DC generators. We have discussed the equivalent circuit of this generator. The only difference from a separately excited DC motor is the direction of current IA changes. Second, the principle of operation is simple. We know that rotating conductor when placed in a magnetic field will actually a voltage will be induced in that coil. And we discussed the terminal characteristics, and in case of a generator, the terminal characteristics means the terminal voltage versus the line current of this machine. In case of a separately excited DC generator, the line current and the armature current are actually same. It's actually line current. Line current and armature current will be same in case of separately excited DC generator. It will be same in case of series DC generators. It will be different in case of shunt DC generators. So these two, and we have discussed the voltage control method of a separately excited DC generator. And instead of discussing the speed control as we discussed in motors, now we are here the terminal voltage that's actually available to us, and we want to control that. We can do that by controlling EA, and EA can be in turn controlled by either changing the flux or the speed of rotation. The speed of rotation is more or less constant because unless there's a gear mechanism connected to the prime mover, we will not be able to change the speed of rotation. But as far as the field of the motor goes, we can easily increase the field voltage or decrease it to change the flux. So that's it for this session. In the next session, we'll be studying the shunt DC generator.